In this video, I will introduce a diffusion video autoencoder for temporally consistent face video editing. To summarize our research briefly, the targeted task is face video editing, which modify a specific attributes of faces in videos. However, all previous methods employ frameworks where each frame is independently encoded and modified, leading to persistent temporal inconsistency problem when editing attributes such as beards. Therefore, we propose a framework that decomposes the video into a single identity feature and motion and background feature for each frame using diffusion-based autoencoders. This framework has the advantage of being able to temporarily consistent editing to entire frames with a single modification of the identity feature. This is a comparison video with existing baselines, and we can see that only our methods produce temporarily consistent results. Now, let's dive into the details of our framework. The diffusion video autoencoder encodes the nth frame into facial related representation G-face and a noise map XT containing background information. Here, G-face is high-level semantic representation, which consists of representative identity feature and nth frame's motion feature. The representative identity is calculated by averaging the identity feature of all frames. Afterward, by using G-face as a condition, the forward process of the diffusion model results in the noise map XT, where only the background information remains since all facial related information is encoded in the condition G-face. The reason we handle only the information excluding the background in the high-level semantic latent space is that the background information has large variance, making it difficult to encode in a low-dimensional space. To achieve perfect decomposition of identity, motion, and background information, we use a pre-trained encoder that can extract each feature without training it. Additionally, for the editing task, which requires nearly perfect reconstruction, we use the DDIM, which has a deterministic forward-backward process. By using the encoding results XT and G-face directly during the reverse process, reconstruction is possible. Moreover, we modify the representative identity feature, compute a new G-face edit, and then proceed with the reverse process to perform editing. To train our model, we use two objectives. The first is the existing DDPM loss, which learns the distribution of face video frames by predicting the noise used in each batch. The second is the regularization loss, which helps ensure clear decomposition between the background and face information. When estimating X0 from noise images generated using different noises, we minimize the differences in the facial part. The first loss encourages useful information to be encoded in the semantic latent G-face, while the second loss reduces the influence of noise on the facial parts, allowing facial related information to be stored in G-face rather than the noise map XT. There are two methods for modifying the identity feature we mentioned earlier. The first method is utilizing the conventional editing method, which is a linear classifier trained for each attribute using CellabAHQ in the identity feature space. By moving the identity feature towards the direction where the trained classifier detects the presence of the attribute, modifications can be made. The second method we devised in this paper is using clip loss, which applies clip loss to the intermediate noise images by significantly reducing the number of diffusion steps for computation cost. Unlike the classifier-based approach, to calculate clip loss, we should update the identity feature and generate image here. To do this, we obtained the editing direction from the identity feature of the first frame of the video and use it into the representative identity space. We first conduct experiments on the reconstruction ability. Thanks to the diffusion model, our method shows better reconstruction ability than the gain inversion method used by baselines. We also evaluate quantitatively and qualitatively to verify temporal consistency. We demonstrate the best qualitative results, and there is a significant improvement in the TG-ID metric, where estimates a global consistency. Furthermore, owing to the reconstructability of diffusion models, it becomes possible to edit wild videos that are difficult to inversion by gain-based methods. Even when faces are occluded by microphones or hands, our model can perform editing effectively. Next, we conduct experiments to examine the results when switching the decomposed features. By confirming that only the switched feature is replaced, we verify that the decomposition is successful. For example, when we replace the noise map XT, which contains background information with random noise, the non-facial parts are randomly altered while excluding the facial information. When we switch the identity feature, we observe that only the identity information of each image is switched accordingly. Lastly, we compare the results when training the model without the regularization loss. In both cases, there are no issues with reconstruction. However, when we replace the noise map XT with random noise, we observed significant change in identity, indicating that the regularization loss helps in separating the features. In conclusion, our contributions are follows. We propose a diffusion video autoencoder that decomposes the video into single time invariant and per frame time variant features, enabling temporally consistent editing by modifying a single identity feature. Furthermore, owing to the diffusion model, we can edit various wild face videos. Lastly, we propose a text-based editing method that applies clip loss to the intermediate noise images. Thank you for listening to my presentation.